February 14, 2024, the Subaru Telescope control room on Mauna Kea, Hawaii. An automated clustering algorithm flags a data anomaly at 70 astronomical units. The operator pauses the telemetry feed. He runs it again. The anomaly persists. A dense ribbon of infrared signatures, faint but statistically undeniable, stretching in an arc across a region of space that every existing model labels as empty. To understand what that operator was looking at, you need to understand what sits at the edge of our solar system. Past Neptune, past the last recognized planet, there is a region of frozen debris. It is called the Kuiper Belt. Most people imagine it as a quiet graveyard, a few dead rocks drifting in the dark. That image is wrong. The Kuiper Belt is a highway. It is a disk of ice and rock that stretches from 30 to 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun. Roughly 93 million miles. The Kuiper Belt begins at 30 times that distance. It ends at 50. The sheer width of it is difficult to process. If you drove a car at highway speed, non-stop, no fuel stops, no sleep, it would take you over 6,000 years to cross it. Light itself, the fastest thing in the universe, takes more than 4 hours to travel from the Sun to the inner edge of the Kuiper Belt. It takes nearly 7 hours to reach the outer edge. When the New Horizons spacecraft flew past Pluto in 2015, the signal confirming the flyby took 4 hours and 25 minutes to reach Earth. That signal was traveling at the speed of light. Every image, every data point from that encounter arrived as a whisper from a place so distant that real-time communication is physically impossible. And Pluto sits near the inner edge. The Kuiper Belt extends far beyond it. And for decades, we assumed we knew what was inside it. We did not. The Kuiper Belt contains an estimated 100,000 objects, larger than 100 kilometers across. Pluto is in there. So is Eris. So is Makemake. These are not small bodies. Eris is roughly the mass of Pluto. Makemake has a diameter of approximately 1,430 kilometers. These are worlds, cold, distant, and largely ignored. But the objects themselves are not the problem. The problem is the pattern they form, or rather the pattern they break. Here is the first anomaly. At 50 astronomical units from the Sun, the Kuiper Belt stops. Not gradually, not like a beach fading into the ocean. It stops like a wall. Astronomers call this the Kuiper Cliff. Beyond 50 AU, the density of objects drops so sharply, it defies every model of planetary formation. The belt should taper off slowly. Debris fields do not have clean edges. Imagine scattering sand across a table. It spreads outward. It thins. It does not hit an invisible line and vanish. But the Kuiper Belt does exactly that. At 50 AU, the objects simply end. No gradual decline, no transitional zone, just a cliff. And beyond it, what appears to be nothing. Astronomers have searched. They have pointed their instruments past the 50 AU line and looked for the gradual thinning that every formation model predicts. It is not there. The drop-off is so severe that some researchers have compared it to a lawn that has been mowed. There is grass, and then there is bare earth. No transition, no scattering. The Kuiper Cliff remains one of the most quietly disturbing features of our solar system. For years, the explanation was resonance. Neptune's gravity, the theory held, sculpted the belt's outer boundary. Neptune orbits at 30 AU. Its gravitational influence can push and pull objects at certain distances. This is true. Neptune does shape the inner Kuiper Belt. But 50 AU is too far. Neptune's resonance cannot reach that distance with enough force to carve such a clean edge. The math does not support it. Something else cut that boundary. Something closer to the cliff itself. Something with mass. Now consider what sits inside this belt. In 2023, The European Space Agency's Cheops satellite confirmed something unexpected about a small world called Quaoar. Quaoar orbits the Sun at about 43 AU. It is roughly 110 kilometers across, smaller than Pluto, unremarkable by most standards. Except for one detail. Quaoar has a ring, a dense ring of particles orbiting around its equator. Rings are not unusual. Saturn has them. Uranus has them. Even some asteroids have faint rings. But every known ring in the solar system obeys a simple rule. It exists inside a boundary called the Roche limit. The Roche limit is the distance from a body within which tidal forces will tear apart a smaller object. Inside the Roche limit, particles cannot clump together. They stay dispersed. They form rings. Outside the Roche limit, gravity wins. Particles aggregate. They form moons. This is not a suggestion. It is a mechanical law. Every ring system observed in decades of planetary science follows it. Quaoar's ring does not. Quaoar's ring sits at roughly 7.4 times its own radius. Its Roche limit is at approximately 3 times its radius. The ring is more than twice as far out as the physics allows. By every model, those particles should have collapsed into a moon millions of years ago. They did not. They remain suspended in a ring, stable and intact, at a distance where stability should be impossible. No current model explains this. The data was checked. It was confirmed by independent observation. The ring is real. Its position is real. And no existing model can account for it. That alone would be enough to redraw the textbooks. But the data showed something worse. Deeper inside the Kuiper Belt, there is a dwarf planet called Haumea. It orbits at roughly 43 AU, not far from Quaoar. Haumea is approximately the same mass as Pluto. But it looks nothing like a planet. It is shaped like an egg, an elongated, flattened ellipsoid, roughly 2,322 kilometers along its longest axis and only 1,761 kilometers along its shortest. It is the most distorted large body in the solar system. And it spins. Haumea completes one full rotation every 3.9 hours. For context, Earth takes 24 hours. Jupiter, the largest planet in our system, takes about 10. Haumea, a body the mass of Pluto, spins at a rate that suggests something struck it with tremendous force, or something is actively torquing it. The spin is so fast that Haumea has been physically deformed by it. Centrifugal force has stretched it into a shape resembling a flattened football. It even has a family of smaller objects sharing its orbit, fragments believed to have been ejected from its surface by whatever event set it spinning. The collision hypothesis is the standard explanation. But the energy required to spin a body of that mass to that speed is extraordinary. And the event would have needed to occur at precisely the right angle, with precisely the right impactor, to produce both the spin and the debris family. The probability is low. The alternative, that an ongoing gravitational influence is responsible, has not been ruled out. It also has a ring, a thin dark ring discovered in 2017. And like Quaoar's ring, it exists in a region that challenges the standard framework. 3 anomalies. A cliff with no explanation. A ring that defies the Roche limit. A dwarf planet spinning at a rate that implies violent interference. Each one, taken alone, could be dismissed as an outlier. Taken together, they describe something else entirely. They describe a region under gravitational stress from an unaccounted source. Consider what this scale actually means. An object capable of carving the Kuiper Cliff, distorting the spin of Haumea, and suspending Quaoar's ring in a mechanically impossible orbit would need to be massive. Not asteroid massive, not dwarf planet massive, planet massive. 5 to 10 times the mass of Earth. And it would need to be close enough to exert persistent force on these objects, yet far enough to remain undetected by every survey telescope in operation. The only place in the solar system where an object of that size could hide is beyond the cliff. In the dark region past 50 AU, in the zone, every catalog marks as empty. In February 2024, that assumption was tested. The data flagged by the Subaru Telescope operator did not describe a single object. It described a structure, a second debris ring, distinct from the classical Kuiper Belt, located between 70 and 90 AU. This is not a theoretical construct. The infrared signatures corresponded to physical objects, thousands of them, frozen, faint, and spread across a band of space 20 AU wide. A band that no formation model predicted. The classical Kuiper Belt ends at 50. The nearest known structure beyond it is the scattered disk, a loosely defined population of objects on highly eccentric orbits. But this second ring was different. It was coherent. It had structure. It had boundaries. It looked sculpted, like the rings of Saturn, where tiny moons called shepherds use their gravity to keep the ring particles confined within neat lanes. Except in this case, there was no visible shepherd, no detected moon, no known body of sufficient mass anywhere near 70 to 90 AU. The ring existed as if something enormous was holding it in place, something that refused to appear in any telescope image. The discovery did not generate headlines. It was reported in technical journals. It was discussed at conferences. It was filed under ongoing survey data. The language used was precise and carefully measured. Clustering anomalies, extended disk population, orbital excess. These are the phrases of a discipline trained to wait for certainty before raising alarms. But the data beneath those phrases was not ordinary. Now add one more piece to the pattern. In 2003, astronomers discovered an object called Sedna. Sedna orbits the Sun, but not like anything else in the solar system. Its closest approach to the Sun is 76 AU. Its farthest point is over 900 AU. Its orbital period is approximately 11,400 years. It is so far away that the Sun, from Sedna's surface, would appear as a bright star, no larger than a pinpoint, no warmer than the background void. Sedna exists in a kind of gravitational no man's land. It is too far from the Sun to be meaningfully influenced by it. It is too far from Neptune for that planet's gravity to have placed it there. It simply orbits alone, in a region where nothing should be orbiting at all. The question of how Sedna got there has never been adequately answered. But Sedna's distance is not the deepest anomaly. The anomaly is its tilt. Sedna's orbit is inclined at roughly 12 degrees to the plane of the solar system. Other detached objects discovered since, including 2012 VP-113 and several candidates identified in recent surveys, share a similar tilt, approximately 15 degrees. They are not randomly scattered. They are clustered. Their orbital poles point in roughly the same direction. This is not what randomness looks like. Randomness distributes evenly. Clustering requires a cause. Gravity is the only force that operates at these distances. Radiation pressure is negligible on bodies this large. Solar wind does not push objects of this mass. Electromagnetic forces are irrelevant at this scale. The clustering of these orbits, their shared tilt, their alignment, requires a gravitational source, a large one, a persistent one, something sitting in the outer dark, pulling these worlds into formation like iron filings around a magnet they cannot see. Stop and consider the full picture. A carved cliff, an impossible ring, a violently spinning dwarf planet, a second debris belt where nothing should exist, and now a family of distant objects, all tilted the same way, all pointing toward the same empty region of space. Each anomaly, alone, is a puzzle. Together, they are a map. And they all converge on one conclusion. The scientific term for this hypothetical object is Planet 9. The name itself is a careful act of classification. It implies a known quantity, a ninth member of a familiar set. It makes the unknown sound administrative. But the data behind the name is not administrative. It is structural. If Planet 9 exists, it rewrites the architecture of the solar system. The Kuiper Cliff is not a natural boundary. It is a carved edge. The second debris ring is not a relic of formation. It is a shepherded structure. Quaoar's ring is not a mystery. It is a symptom. Haumea's spin is not an accident. It is a consequence. Sedna's tilt is not an outlier. It is a signature. And the mass required to produce all of these effects simultaneously is not small. Current models estimate between 5 and 10 Earth masses. An object that size, at a distance of 400 to 800 AU, would have an orbital period of 10,000 to 20,000 years. It would move so slowly against the background stars that it would be almost indistinguishable from them. It would emit no visible light. It would reflect almost none. At that distance, the sun's light is roughly 160,000 times dimmer than it is on Earth. Finding this object with a telescope is like searching for a black marble on a black floor in a dark room the size of a continent. And yet, the gravitational evidence keeps accumulating. So why has no one confirmed it? This is where the institutional framework becomes relevant. NASA's budget for outer solar system surveys has historically been a fraction of its planetary defense allocation. The Wide Field Infrared Survey Explorer, or WISE, was the most capable all-sky infrared survey ever conducted. It mapped the entire sky twice. It found nothing matching a Planet 9 signature, but WISE had limitations. Its sensitivity dropped sharply at the wavelengths a cold, distant planet would emit. A body at 500 AU, with a surface temperature of roughly 40 Kelvin, would radiate almost entirely in the far infrared. WISE was not optimized for that band. The Vera C. Rubin Observatory, scheduled for full survey operations, may change this. Its legacy survey of space and time will map the southern sky repeatedly for a decade. It is designed to detect faint, slow-moving objects. But the survey is enormous. The data pipeline is enormous. And astronomy, by design, does not rush. Extraordinary claims require extraordinary verification. A discovery this large cannot be announced on preliminary data. It must survive peer review, replication, independent confirmation. The process is slow not because the conclusion is being suppressed, but because the stakes of being wrong are enormous. So the language stays cautious. The papers say consistent with. The conferences say candidate. And the telescopes keep scanning. Meanwhile, the data accumulates, quietly, relentlessly, without fanfare. The second debris ring between 70 and 90 AU has now been confirmed by multiple independent survey teams. The orbital clustering of detached trans-Neptunian objects continues to hold under expanded data sets. Quaoar's ring has been reobserved and its position reconfirmed. Haumea's spin rate has not changed. Sedna continues on its vast, lonely arc, tilted away from the plane of the solar system by an angle that only gravity can explain. Every new data point strengthens the same hypothesis. Something may be out there, something with the mass of a giant planet, something that has been shaping the outer solar system for billions of years while remaining invisible to every instrument we have pointed at the sky. The anomalies do not prove it, but they refuse to go away, and each new survey adds another line to the same argument. The question is shifting. It is no longer whether the anomalies are real. They are. Every data set confirms them. The question is what explains them all at once, and there is a gap forming. A gap between what the data increasingly suggests and what any institution is willing to formally declare. The Kuiper Cliff is still called a distribution feature. Quaoar's ring is still labeled an anomalous structure. The orbital clustering of Sedna and its siblings is still described as statistically interesting. This is not evasion. This is how science operates under pressure. Extraordinary claims require extraordinary proof. And proof of a planet no one has photographed does not arrive in a press release. It arrives slowly, in fragments, across decades of survey data. But the fragments keep arriving, and they keep pointing in the same direction. The solar system you were taught, with 8 planets and a clean boundary, may not be the solar system that exists. There may be a 9th body, it may be massive, it may be dark, and it may have been rearranging the frozen edge of our solar system for longer than any living thing has existed on Earth. February 14th, 2024, the Subaru Telescope control room. The operator stares at the flagged anomaly at 70 AU. He knows what the clustering algorithm found. He knows what it implies. He files the data under the proper classification code. He resumes the telemetry feed. The telescope continues its sweep of the dark. Somewhere beyond the cliff, something massive continues to shape it.